Good morning. My name is Jerzy Wrona and I am a senior researcher at Singulus Technologies. This presentation is part of the NICKEFFECT project focused on replacing platinum-based materials with nickel-based alternatives for energy and digital storage applications. Today, I will discuss the design of PT-free perpendicular MTJ structures for MRAM applications using cobalt-nickel-based synthetic ferromagnet structures. The presented work was performed in collaboration with the AGH University of Krakow, particularly the group of Professor Skowroński involved in nanopillar fabrication and characterization. This seminar is divided into 6 main parts. First, I will briefly introduce the NICKEFFECT project and explain the motivation for developing PT-free materials for next-generation MRAM technologies. Next, I will present the operating principle of MRAM and discuss the role of magnetic tunnel junctions, MTJs, in spintronic memory applications. In the third part, I will introduce the Singulus Technologies deposition platform used for the fabrication of the multi-layer MTJ stacks investigated in this work. The main part of this presentation focuses on MTJ stack application at the wafer level. This section includes magnetic characterization using VSM measurements, electrical characterization using CIPT, and dynamic characterization based on FMR measurements. Afterwards, I will present the performance of the fabricated MTJ nanopillars, including STT switching behavior, a bit error rate (BER) analysis, thermal and thermal stability measurements. Finally, I will summarize the main results and discuss the potential of PT-free cobalt-nickel-based MTJ technology for a future low-power and sustainable MRAM application. NICKEFFECT is an EU research project focused on the development of nickel-based alternatives for platinum group metals used in energy and digital storage technologies. The main objective of the project is to reduce Europe's dependence on critical raw materials by replacing PT-based systems with more abundant and accessible nickel-based materials. One of the key motivations behind the project is the highly uneven global distribution of the platinum group metals. As illustrated in the chart on the right, most PGM production is concentrated in South Africa and Russia, while the European Union contributes only a very small fraction of the global supply and therefore remains strongly dependent on imports. To address this challenge, NICKEFFECT focuses on applications such as water electrolyzers, fuel cells, and spintronic memory technologies, including MRAM. MRAM is considered one of the most promising candidates for future low-power and energy-efficient memory technologies, particularly for AI and data-centric applications. In this presentation, I will focus on PT-free cobalt-nickel magnetic multilayers designed for next-generation perpendicular MRAM devices. MRAM, or Magnetoresistive Random-Access Memory, is a non-volatile memory technology that stores information using magnetic states instead of electric charge. Unlike conventional volatile memories, MRAM combines non-volatility with high speed and low standby power consumption, making it one of the most promising candidates for future energy-efficient embedded memory technologies. The basic element of MRAM is the magnetic tunnel junction, or MTJ, shown on the left side of the slide. The MTJ consists of 2 ferromagnetic layers separated by a thin MgO tunnel barrier. The reference layer has fixed magnetization, while the free layer can switch its magnetic state. In modern perpendicular MRAM structures, the magnetization is oriented out of plane due to the perpendicular magnetic anisotropy. Information is encoded through the relative orientation of magnetization in the two layers. The parallel state corresponds to low resistance, while the antiparallel state exhibits high resistance. Depending on the device design, these states can represent logical 0 or 1. The resistance difference is described by the tunnel magnetoresistance ratio, or TMR, shown at the bottom of the slide. A high TMR value is essential for reliable device readout. The schematic on the right illustrates STT switching, currently the dominant commercial MRAM technology. As electrons pass through the reference layer, the current becomes spin polarized along the reference layer magnetization. The spin polarized current exerts spin transfer torque on the free layer and can switch its magnetization direction. One current direction favors the parallel state, while the opposite direction favors the antiparallel state. During readout, a much smaller sensing current is used to measure the resistance without disturbing the stored information. Within the NICKEFFECT project, the MTJ stacks were fabricated using the Singulus Technologies MTM deposition system, which was especially developed for MRAM and magnetic sensor applications. It is based on a linear dynamic deposition technology. In this approach, the wafer moves linearly beneath a rectangular sputtering target during the deposition process. The rotating drum contains 10 sputtering targets, enabling sequential deposition of complex multi-layer stacks without breaking vacuum. In the center part of the drum, two dedicated magnet configurations are used for ferromagnetic and non-ferromagnetic material deposition. The deposition system supports both DC and RF sputtering processes and enables deposition of ultra-thin films with excellent thickness and interface control. Such a machine design enables highly reproducible growth of complex multi-layer thin films and provides industrially compatible processing for advanced MRAM and sensor technologies. The MTJ stack design starts with the development of the bottom multilayer system, B-sieve, with strong perpendicular magnetic anisotropy, which is subsequently used for the formation of the complete sieve structure. A suitable seed layer is required to ensure the proper growth, texture and crystalline quality of the cobalt-nickel multilayer system. In a well-designed MTJ stack, the top part of the sieve, T-sieve, is ferromagnetically coupled to the reference layer, RL, through the RL spacer in order to stabilize the RL switching behavior and create a well-defined free-layer switching plateau between -HX and +HX, as shown in the center switching schematic. To achieve optimal switching behavior, the sieve is further optimized through the adjustment of cobalt and nickel layer thicknesses, the RKKY coupling strengths mediated by the ruthenium spacer, as well as the RL spacer thickness, which strongly influences the switching stability of the reference layer. The MGO-based tunnel barrier separated by the reference layer from the free layer, FL, enabling spin-dependent tunneling and high TMR ratio. VSM measurements were performed to optimize the cobalt-nickel multilayer system used for the sieve structure. The upper row shows out-of-plane hysteresis loops, while the lower row presents in-plane measurements. The first column illustrates the influence of the seed layer on the magnetic anisotropy of the cobalt-nickel multilayer system. A strong perpendicular magnetic anisotropy is obtained for the copper seed layer, whereas the ruthenium seed results in predominantly in-plane magnetic behavior. The middle column presents the cobalt thickness optimization for a fixed nickel thickness of 0.6 nanometer. The strongest PMA and the most favorable switching characteristics are observed for cobalt thicknesses in the range of 0.25 to 0.30 nanometer. The right column shows the nickel thickness optimization performed for a fixed cobalt thickness of 0.25 nanometer. The optimal magnetic properties are obtained for nickel thicknesses between 0.5 and 0.7 nanometer. Based on the VSM optimization results, a multilayer system with 0.6 nanometer nickel and 0.25 nanometer cobalt was selected for the next experiment. The optimization of RKKY coupling in the cobalt-nickel synthetic ferrimagnet system separated by a non-magnetic ruthenium spacer was performed in 3 stages. In the first step, the ruthenium spacer thickness was optimized. As shown in the left column, the effective coupling field, Hx, exhibits an oscillatory dependence on the ruthenium thickness. The maximum coupling strength, corresponding to the second RKKY maximum, was obtained for the ruthenium thickness of approximately 0.9 nanometer. The second maximum was selected due to the wider thickness tolerance window compared to the first coupling maximum. In the second stage, the thickness of cobalt layer adjacent to the ruthenium spacer was optimized in order to increase the effective RKKY coupling. Stronger coupling improves the collective switching behavior of the sieve and enhances the stability of the RL sieve system. As shown in the middle column, the value of Hx strongly depends on the cobalt thickness at the ruthenium interface. For the reference structure, without additional cobalt, deco S0, the coupling field reaches approximately 2600 Ørsted and increases to nearly 3800 for the additional 0.2 nanometer cobalt layer. Further increase of cobalt thickness leads to a reduction of the effective coupling field. The right column presents the dependence of Hx on the number of repetitions of the cobalt-nickel multilayer in the top part of the sieve structure, for different numbers of repetitions in the bottom part of the sieve, B sieve. The coupling field depends on both the bottom and the top sieve repetitions, with significantly stronger influence observed for changes in the number of repetitions in the top multilayer section. The maximum coupling field of approximately 7500 was obtained for the 2 repetitions of the top multilayer. In practical MTJ structures, the top part of the synthetic ferrimagnet, T sieve, is ferromagnetically coupled to the reference layer RL of the tunnel junction through their properly optimized RL spacer. Strong coupling between the T sieve and RL is crucial for stabilizing the reference layer and preventing independent RL reversal. The main design challenge is to obtain a well-compensated sieve structure for which the magnetic moments of the bottom and top sieve parts are almost equal. In the non-compensated sieve structure, imbalance between the magnetic moments of the 2 sieve parts may destabilize the coupled switching behavior, leading to the appearance of intermediate switching states in the hysteresis loop. This results in a reduction of the operating window and degradation of the switching characteristics, significantly limiting the application potential of the MTJ structure. As illustrated in the schematic, The magnetic moment compensation can be achieved by adjusting the thickness or the number of cobalt-nickel multilayer repetitions in the top and bottom parts of the sieve structure. This slide presents examples of the optimization of the sieve RL switching behavior based on hysteresis loops measurement for the complete MTJ stack. The optimization was performed for the full MTJ structure, including the free layer, whose relatively low anisotropy does not affect the analysis of the sieve RL switching characteristics. The left part shows the influence of the number of repetitions in the bottom part of the sieve, BLAM, on the switching characteristic of the complete stack for a fixed number of repetitions in the top part of the sieve. For BLAM equals 6 and 7, the most well-defined free-layer switching plateau was obtained, corresponding to the dark blue or purple curves. The middle graph presents the effect of simultaneously increasing the number of multi-layer repetitions in both the bottom and top parts of the sieve structure. As shown, increasing the number of repetitions improves the magnetic anisotropy and stabilizes the switching behavior of the sieve RL system. The graph on the right compares two different RL spacer configurations. Replacing the standard tungsten spacer with a composite tantalum-cobalt tungsten spacer results in a significantly improved switching characteristics of the sieve RL system and better stabilization of the reference layer. After optimization of the sieve RL magnetic system, the next step was integration of the full MTJ stack, including the composite free layer. The free layer was based on a dual FCB structure, separated by a thin tungsten spacer and optimized to provide strong PMA, high TMR, low switching current, and good thermal stability. This full-stack integration enabled further optimization of the MTJ electrical performance prior to nanopillar fabrication. The presented MTJ architecture was designed to achieve industrially relevant performance while eliminating the need for PT-based magnetic multilayers. The integration of the full MTJ stack, the next step was optimization of the spacer layers in order to maximize the TMR ratio. This slide presents the influence of tungsten and tantalum spacer thicknesses on the MTJ electrical performance for different annealing times. The left and middle graphs show the optimization of the tungsten spacer thickness used respectively in the reference layer spacer and free layer spacer. In both cases, the highest TMR values, exceeding 130%, were obtained for a tungsten thickness close to 0.25 nanometer after extended annealing. Further increase of tungsten thickness leads to a gradual reduction of the TMR ratio. The graph on the right presents the optimization of the tantalum spacer thickness in the RL spacer region. The best transport properties were obtained for tantalum thickness in the range of approximately 0.1–0.25 nanometer. For thicker tantalum layers, a strong degradation of TMR is observed, particularly after longer annealing times. These results demonstrate that precise spacer engineering plays a crucial role in achieving high TMR values and stable electrical properties of the MTJ stack. The next optimization step focused on the reference layer composition and thickness in order to further improve the TMR ratio while maintaining favorable RA values. This slide compares MTJ structures based on the two different FICO-B reference layer compositions. The standard 60-20-20, FCB60, and an 53-17-30, FCB53, containing 30% of boron. The graph on the left presents the dependence on the TMR and array on the thickness of the FCB60 reference layer. The highest TMR values, around 135%, were obtained for RL thicknesses close to 0.9 to 1 nanometer, while array product remained in the range of approximately 12 to 13 micrometer squared. The graph on the right shows the corresponding optimization performed for FCB53 reference layer. In this case, even higher TMR values exceeding 140% were achieved for RL thicknesses around 1 nanometer, while simultaneously maintaining lower array values compared to the standard FCB60 reference layer. These results indicate that the iron-rich FCB53 composition enables simultaneous improved of both TMR and array characteristics compared to the standard FCB60 reference layer. The final optimization step focused on the thickness of the first layer in the dual FCB three-layer system, while the thickness of the second one was kept constant at 0.5 nanometer. The objective was to maximize the TMR ratio while maintaining favorable MTJ transport properties. The graph shows the dependence of TMR on the thickness of the first FCB layer for different annealing conditions. For all investigated annealing processes, the TMR ratio exhibits a clear maximum for a FCB thickness close to 1.3 nanometer. Further increase of the FCB thickness results in gradual degradation of the TMR ratio, which is associated with weakening of the perpendicular magnetic anisotropy and degradation of the spin-dependent tunneling properties at the FCB-MGO interface. The highest TMR value, reaching approximately 140%, was obtained for FCB thickness of 1.3 nanometer after annealing at 370 degrees C for 2 hours. The array product shows only minor variation with the FCB thickness, confirming stable tunnel barrier quality during the optimization process. These results demonstrate the strong influence of the three-layer thickness and annealing conditions on the MTJ transport properties and confirm the importance of precise three-layer engineering for achieving high-performance MRAM structures. Magnetic resonance measurements, FMR, were performed to investigate the dynamic magnetic properties of the final optimized MTJ stack. The measurements enabled identification of the resonance modes associated with the synthetic ferrimagnet, reference layer, and free layer, as well as extraction of key magnetic parameters relevant for STT-MRAM operation. Panel A presents the hysteresis loop of the complete MTJ stack, showing the sequential switching behavior of the free layer, reference layer, and sieve system. Panel B shows the frequency versus field dispersion relations obtained from the FMR measurements for the RL, FL, and sieve resonance modes. The color map in panel C presents representative FMR spectra measured over a broad magnetic field and frequency range. Several resonance branches can be identified corresponding to the dynamic response of the individual magnetic subsystems within the MTJ stack. By fitting the dispersion relations, the effective magnetic parameters were extracted. The effective magnetization, anisotropy field, anisotropy energy, and damping parameter are summarized in the table on the right side of the slide. The optimized three-layer exhibit low damping together with strong perpendicular anisotropy, which are desirable for low current and high-speed STT switching. At the same time, the sieve and RL systems remain strongly stabilized, supporting reliable operation of the complete MTJ structure. After optimization of the MTJ stack at the wafer level, the structures were patterned into nanopillars with diameters ranging from 500 down to 80 nanometers. The fabricated devices were subsequently electrically characterized in order to evaluate the stability for STT MRAM applications. The optical image shown on the upper right presents the layout of the fabricated MTJ device array on the wafer. A magnified view of a single device is shown below, illustrating the MTJ pillar located between the top and bottom electrodes. The graphs on the left present representative magnetoresistance loops measured for different MTJ pillar diameters. Clear switching between the parallel and antiparallel magnetic states is observed for all investigated device sizes, confirming reliable MTJ operation after nanopatterning. High TMR values reaching up to 140% were obtained together with reference layer stability fields exceeding 250 millitesla, demonstrating strong stabilization of the optimized sieve RL system even at nanoscale dimensions. These results confirm that the optimized PT-free MTJ stack maintains excellent magnetic and transport properties after device fabrication, and it's suitable for further STT switching and reliability investigations. After fabrication of the MTJ nanopillars, spin transfer torque switching measurements (STT) were performed to evaluate the switching performance of the optimized PT-free MTJ devices. The graph on the right presents representative current-induced switching loops measured for MTJ pillars with diameters of 80 nanometers in red and 160 nanometer in blue. Clear switching between the parallel and antiparallel resistance states is observed for both device sizes, confirming efficient STT-driven magnetization reversal of the free layer. A noticeable shift of the switching loop is observed due to the interaction between the free layer and the reference layer system. Nevertheless, reliable bipolar switching is maintained over a broad current range. The optimized MTJ devices exhibit switching voltages below 0.5 volt and switching current densities below 3 megaamp per centimeter square, which are highly favorable for low-power STT MRAM application. In addition, the reliable switching operation was achieved for pulse width longer than approximately 5 nanoseconds, as illustrated in the inset. These results demonstrate that the optimized PT-free cobalt-nickel-based MTJ stacks enable efficient and reliable STT switching at nanoscale dimensions. In addition to static and dynamic switching measurements, the thermal stability and reliability of the optimized MTJ nanopillars were investigated. Thermal stability is one of the key requirements for reliable STT MRAM operation, since it determines long-term data retention and switching robustness. The analysis was based on statistical fitting of the switching probability distributions for both switching directions. The experimental data were fitted using a thermally activated switching model. The switching probability distributions presented on the right were measured as a function of magnetic field and switching current. From the fitting procedure, the active thermal stability factor delta and the intrinsic critical switching currents were extracted. The optimized device exhibit thermal stability factors exceeding 50, together with the representative intrinsic critical switching currents in the range of approximately 200 to 300 micrams. This demonstrates a favorable balance between thermal stability and switching efficiency, which is essential for practical STT-MRAM applications. The graphs on the left present the measured BER, or bit error rate, characteristics, together with switching statistics as a function of applied voltage. The experiment starts at the low voltages amplitude and continues to the high end. BER equal 1 means all switching attempts had been unsuccessful. BER equal 0 means all switching attempts had been successful. For the outermost points in the right graph, 10 to the power of 8, there is no corresponding point in the BER plot. At those voltages, all switching attempts had been successful. In summary, the NICKEFFECT project successfully demonstrated the feasibility of PT-free MTJ technology based on cobalt-nickel synthetic ferromagnet multilayers. The developed sieve system provided strong stabilization of the reference layer with switching fields exceeding 2500 Ørsted. After optimization of the complete MTJ stack, excellent electrical and magnetic performance was achieved, including TMR values up to 140%, RA values around 8 ohm micrometer square, low damping parameters close to 0.011, and thermal stability factors exceeding 50. The fabricated nanopillar devices also demonstrated efficient STT switching with switching current densities below 2.6 megaamps per centimeter square and average switching voltages around 0.35 volt. In addition, reliable device operation was confirmed through endurance measurements exceeding 10 to the power of 8 error-free switching cycles. These results demonstrate that the PT-free cobalt-nickel-based MTJs can provide high performance, low power, and thermal stable MRAM devices while reducing dependence on critical platinum group metals. The presented technology therefore represents a promising route towards sustainable, energy-efficient, and industrial-compatible next-generation MRAM solutions for future AI and data-centric applications. The presented results were published in scientific reports in 2025. This appendix summarizes the key MRAM performance requirements and compares conventional PT-based technology with the developed PT-free cobalt-nickel-based approach. The presented results demonstrate that the PT-free MTJ stacks can achieve performance comparable to state-of-the-art PT-based MRAM while eliminating the need for platinum group magnetic multilayers. Thank you very much for your attention. I would also like to acknowledge all partners of the NICKEFFECT project for their collaboration and support.